So today I want to talk about advanced methods for visual synthesis and how they can eventually be used to learn models with the ultimate goal of understanding our visual world. But before that, let's start at the beginning and ask the question, what actually the purpose of vision is. What's vision all about? What is human vision in particular all about? I believe it's not just seeing, and it's also not just enjoying sights, art, or a sunset. It's definitely not there for watching TV, and for sure, not for ramping up some numbers on ImageNet. So what is vision all about? And in particular, what is human vision about? Let's say in contrast to the vision of a frog. It's not about detecting objects. And I believe it's also not just there for avoiding danger, although that's important, because these are much too small of a task. So what is vision ultimately about? I believe it's nothing less but understanding the world. Understanding the world by seeing, that means grasping the world without touching. And with that comes the enormous inverse problem of vision and intelligence, and artificial intelligence in particular. That is, think of our brain as being held captive in a box, yeah, with a tiny slit towards the outside, our senses, vision being one of the more profound ones there. And then our brain tries to answer the old Gestaltist question, why do things actually look as they do, like Kafka and Köhler and Wertheim and so on asked. And by means of our senses, we can try to make sense of the world. By means of perception, get a hold of what's out there. And in addition to that, I believe equally important is our ability to predict what's out there. Not just the future, but also predict the entire stimulus, a given part of it, which is, in our language, controlled hallucination. So I believe that we're all hallucinating all the time. That is, we're imagining what's out there. It's only that when we agree on our hallucinations, that then we call them reality. But these hallucinations are actually just a representation of the world. They aren't the reality in themselves. So let's contrast these two parts here, perception and prediction. And with prediction, I'm aiming for a little bit broader term than one might think. I'm thinking of prediction more in the sense of predictive coding that we're used to from the neurosciences, starting off with Hermann von Helmholtz's work on unconscious inference, work by Rama Ballard, and so on. So really in the sense of constantly generating and updating a mental model of the environment, one that tries to sort of complete the stimulus that comes from the perception, somewhat in the sense of constructive cognitivism by Piaget, for instance. So perception. Perception wants to answer direct questions such as what is there, what is not there. So in our language as machine learners, discriminative tasks, regression problems, classification problems, where we want to discriminate between different models that there might be of the world. Let's say, is this a bicycle or is this a car? You have two models for explaining what's out there and you want to discriminate between these two. Contrast that to this predictive understanding where we want to predict parts of our stimulus given other parts of the stimulus or even future stimuli that might come in. And that in our language would be more like the generative world, where we want to synthesize the stimulus or synthesize the future stimulus. And it's interesting that the link between the rich stimulus from the outside and the compact abstract representation that is essentially established in a top-down processing that perception is inverted in the predictive world, where we're having a bottom-up process where with tiny bit of information, you want to make up the entire rich stimulus. There's a lot to say here about the difference between the models that perception deals with as opposed to those of prediction and how much richer they are. But I guess I skipped this in the interest of time. So as AD said, my research interests, or those of my group, are in the fields of metric learning, especially out-of-data generalization, transfer learning, and the like, interpretable models that try to explain deep learning models and the invariances that they have. I believe that self-supervision is a very important learning paradigm because there will be in the future much more data than there will ever be labels. And last but not least, controllable visual synthesis. And the last I've been asked to talk about, and this is what the talk here will concentrate on, only the last part of controllable visual synthesis. So let's get into that. If we want to synthesize scenes, it's entirely important to model their contextual relationships, and especially the long-range ones. If you're taking this image here, without such contextual relationships, you're just getting a bulk of stuff, but the impression of the scene is entirely lost. So what do we need to represent a scene? We need to model local structures such as texture and appearance, and we need to model the global structure of the scene, the perspective that we have, relationships between parts of the object that give us object consistency, that the color here of the giraffe on the neck and the legs is kind of consistent with another. Consistent illumination of a scene, object interactions, foreground, background interactions, and so on. And an effective approach, or an approach to actually modeling the contents of such a scene have been autoregressive models that factorize the probability distribution of an entire scene. And there are two ways to now deal with this autoregressive sampling approach. And one would be convolutional neural networks. And they are very effective by means of the inductive bias that they have, and that is the local convolution. The local convolution operation focuses all the information on what's within the kernel. We know that we can stack a whole lot of kernels on top, and with that we can effectively increase the size of the receptive field, but only indirectly, and the most direct interaction will always be that within a single kernel, and that we cannot infinitely scale. And that's why the natural inductive bias here leads to local interactions being favored or modeled by a convolutional network. Contrast that to transformers, autoregressive transformer models, which are great and powerful models for representing long-range interactions in a scene. Things which are far away we can bring together, but this comes at a high computational cost, and them being computationally intractable for large data. So here we have a quadratic complexity due to the attention mechanism in the number of pixels as opposed to the convolutional kernels, which are very computationally effective. And what we now want in this taming transformers approach is combine the benefits of both approaches, combine the powerful long-range interactions from transformers with the local inductive bias, which leads to efficiency of convolutional approaches. So in essence, we are proposing to utilize a convolutional model, which we coined VQ gun for the local structure, with an autoregressive transformer to model the global structure. And the VQ gun approach is an extension of VQ BAEs, which used to be there beforehand. We take our images here, divide them in local patches, for instance, and these patches are then encoded by means of a convolutional encoder. We then adopt the standard theme these days of going for a quantized representation. So we're having a discrete codebook, and we need to have straight-through gradient estimation when we backpropagate through that, and then run this through a decoder again. This gives us the local structure very effectively by means of the convolutional operation, but only within individual patches. We deliberately limited this here to individual patches, no extensive receptive field or whatever else. The global structure is then, just a second. So in contrast to VQ BAEs, we replaced the L1, the local pixel-wise loss, with a perceptual loss, and here also added patch-wise adversarial loss to trade the realism against the perfect reconstruction. And to introduce now global relationships, we utilize transformer, autoregressive transformer models, which then takes these individual cells that we're having here and wanting to predict then the contents of the next cell given the previous cells, and essentially utilize maximum likelihood learning. You can, in addition to that, prepend an additional conditioning on the textual side, so that you can do text-to-image and so on. But I have more on that on the following slides. So many of you might have, or I guess all of you have seen that VQ-GAN is not the only approach, but after we published that, other approaches came also around, like the DALI model, for instance. And if you contrast both approaches here, although we published ours earlier, you can see that the DALI approach with the same complexity due to this VAE, the restriction of VAE, typically is a significantly more blurred representation. And if you take ours due to the transformer approach being very effective for modeling long-range interactions, we can actually reduce the complexity here by a factor of 4, and the local structure is still reasonably preserved, and a reduction in compression here by a factor of 4 means that the overall computational gain is then a factor of 16, which enables the approach to do this high resolution scene synthesis in an autoregressive fashion. So you can then take a scene and build this up patch by patch, synthesize new scenes where we can sort of dream about without being able to travel around the world, and here enjoy the sights that this model can actually generate. Now, in addition to synthesizing such scenes, we can also condition on a whole lot of sort of conditioning tasks, such as class conditional synthesis here for ImageNet, where you take individual classes and then generate images for them. You can condition on depth, on layout. We have this super resolution where you condition on a low-res image and then generate high-res images, or you condition on part of a scene and then synthesize the rest of the scene. Here's an example of the depth-to-image synthesis and then sampling from this process, and that is what then eventually comes out. You might ask yourself, since the VQ-GAN and the VQ-VAE seem to have some things in common, how they actually compare against another. I mean, already said that we extended VQ-VAE, but here's a direct comparison, and sure enough, I mean, the restrictions of VAE you see here again, like being more blurred than our approach, and we also provided a quantitative comparison with VQ-VAE2. They just reported an approximate FID, and if you compare this to the results that VQ-GAN has, you see here that VQ-GAN also improves on VQ-VAE2 significantly. Tiny look out to some recent work that we published. We wanted to get the conditioning even coarser, so to speak, rather than requiring a per pixel annotation like a semantic map. We here present an approach which is just a bunch of bounding boxes. So you can just utilize bounding boxes as a conditioning, and the approach then fills in all the details. That means that just the tokens for our transformer model are now changed so that they contain the class information and the bounding box coordinates, and then the model actually synthesizes the rest. And with such an approach, you can take a scene like this one here, take bounding boxes without pixel-wise annotation, and then have the model fill in the blank and synthesize the scene. What I find, however, much more interesting is what artists have been doing with the VQ-GAN model due to its computational effectiveness. It's open for everybody to utilize. The code is out there, and a lot of people have scripted code around that. Combine this with the clip model. We all know that transformers have also been very powerful on text, and the clip model is taking this part then. And if you combine both with another, then you have a powerful model to do text to image synthesis. And it just dawned to me when I presented this talk again, looked at Twitter under this hashtag for VQ-GAN, what amazing art others have put together. So I'm taking absolutely no credit for these images. I'm just astounded what people can actually put together and the quality of results that you get. So you just need text input, something here, bird made of worms, and this is what then such a model actually spits out. And it is, as I said, very effective. So I've seen that others have put together a mini version of DALI, which is like 20 times smaller than the original DALI approach, by adopting our VQ-GAN approach. So if you want, you can just try this out under these links. So let me summarize. The Taming transformers approach that I've just shown combines the efficiency of convolutions for representing local context with the power of autoregressive transformers for representing long-range interactions. The complexity of transformers is by that tamed because the local convolutions take care of a lot of sort of local information, and we combined adversarial with likelihood learning here. This all led to a significant increase of efficiency. So here's 16x decrease of computational cost, and that allows us to do high resolution image synthesis. Now, so far we've stayed in the 2D world, and then we ask ourselves, can we actually move to the 3D world and do novel view synthesis, where you're just presented a single static image, you're having no 3D prior model, it's geometry free, and you're just saying how you would want to change your viewpoint and then render a new view accordingly. And this is what this approach that I'm now going to show at, which is just going to come out at ICCD this year, is doing. Code is here available. But in order, before going in there, we need to contrast the whole sort of juggernaut of different novel view synthesis approaches that there are out, and see like how they actually differ from another. So the first question that we have is, what do we have actually provided? Only a single view based on which we then have to generate novel views? Or do we have multiple source views provided, like the cyan ones that you see down here in the Rikla and Colton paper? The next question is whether we really want to synthesize a novel view or a not so novel view. So essentially, is this true extrapolation or interpolation? And you can see here that some of the reddish cameras are kind of close to the cyan ones, and even the others, given the multitude of views that we have here, it's kind of at least questionable to what extent this is a valid extrapolation. However, we are concentrating on a single view approach, and the camera then being having a large or showing a large change of viewpoint, so a true extrapolation. Next question is, do we have explicit geometry provided, a 3D model of our world that we then just need to estimate the parameters for? Or do we want to implicitly map a source view pixels onto a target view, so 2D pixels on 2D pixels? And the last questions here are just like, do you want to have control over the synthesis, or do you just want to synthesize something arbitrary, much like generative adversarial networks in their early rounds have done? But in novel view synthesis, typically people evidently want to have control. And last, natural scenes or limited to an artificial world. And in all of that, we're here on the left side. So we want, given a single view, extrapolate to a completely novel view, which is very far away from the original view. We want to have an implicit model without requiring a 3D prior of the scene that we're looking at, or anything that we could just utilize to estimate parameters. And we want evident control and this thing being applicable to natural scenes. So here's how it works. Given an input image, if you have a medium change of viewpoint, approaches like Synthin and so on provide you with reasonable outcomes. But when you have a large camera change, these approaches have problems rendering the scene. And it's no wonder why. The novel view, the destination view here, is underdetermined when you allow for an arbitrary large transformation, extrapolation, and only a single view. It's hard to predict what's there. You cannot deterministically estimate the outcome. And that's why we embrace a probabilistic approach, where we have a transformer model, synthesize several reasonable outcomes, given the source view and the change in viewpoint. And this probabilistic approach then samples the most likely outcomes of this scene. And this approach works without any, that's why I say here implicit 3D, without requiring any 3D information about the scene. More on that in a slide. To estimate this probability distribution, we are facing a problem essentially. We need to learn a 3D relationship between 2D images and the viewpoint change. So in essence, you have a source view, 2D, a target view, 2D, and you have a change in viewpoint. And if you now want, given your source image, to change the viewpoint, you somehow need to estimate the 3D relationship between this change between source and target view and your camera matrix, your change in viewpoint. And there are, in principle, two approaches two ways that we could actually sort of walk down. Either an explicit approach, where we establish a 3D model and then estimate its parameters. Most CNN approaches, due to their locality bias, actually adopt this, and you don't have long-range interactions, or with a CNN, you have a hard time actually establishing them. So you then utilize the 3D model to give you long-range consistency and estimate the parameters. And the other would be an implicit approach, where you take 2D pixels for the source and the target view, and you have a direct mapping from your source to your target view, and utilize the powerful transformer architecture to learn the long-range interaction. And we'll see that the powerful transformer models are capable of implicitly establishing a 3D consistency and long-range interactions without requiring 3D models. So in essence, you're taking a source view, you're having your viewpoint change here, which is this T matrix, and we encode both of that in embedding, the desired change in viewpoint, and an encoding of the source theme. Shuffle both of that into a transformer model without any prior 3D model of the world, and then in autoregressive fashion, given the source image and this change in viewpoint, in autoregressive fashion, building the destination views. Contrast that to an explicit 3D model. There you explicitly either need the depth of the scene or a warp of between source and target view, or both, and you inject this into your encoding as well. And then based on this warp version and or the depth estimate of the scene, you build the destination image. So we want here to have the bottom approach, but we compare both and different ways to actually get 3D prior geometry into the game. And then utilize the same transformer architecture, and we'll see that the bottom one here is actually beneficial. So here's how it goes. We again utilize the humble VQ GAN approach to represent a source image and a target image as well, by means of, again, this discrete representation. Then we apply a standard positional encoding and get an image embedding by running it here through a neural network, G, to give us our image embedding. The same we have to do for the source image together with the desired viewpoint change, T. So source image and viewpoint change also run through a different neural network, F, to give us another embedding. Both embeddings we will eventually shuffle into a transformer model, which then completes the destination view. And here is the critical part. This function F here could now embrace a depth estimate of the scene, could utilize an explicit warp, a 3D model of the scene, lots of 3D inductive biases. And we will evaluate different functions F here, which will give us the opportunity to utilize extra information from prior models about the scene, or doing it without, where we essentially just having source and target and mapping that onto an embedding. So it's all in this function F. Now, we take source and the transformation and the viewpoint change, source and viewpoint change, and then we want to render the destination view in an autoregressive fashion. That means both of them go into a transformer model, and the transformer model then again autoregressively completes the destination view by predicting here the next cell and on it goes. You train this with max data log likelihood, and then you get this. Given a static 2D image and your change in viewpoint that you would want to have, the model has implicitly, without having any 3D information about this flat 2D image, implicitly rendered or implicitly understood the 3D geometry and can then complete this scene from there. And then you can go into a scene and create multiple additional viewpoints. This is one of our offices here, where students sitting that created that, and then you can zoom in. And the approach evidently has now to hallucinate things that it has not seen beforehand. And this all works by taking during training a lot of individual images and a viewpoint change, and then learning some consistencies between these so that you can apply it to a novel scene. I said that the model implicitly learns geometry without being provided with that. So what you can, for instance, do is ask the model without providing it with depth information afterwards, what it thinks about the depth of an individual's pixel. And you can do this for different layers of the architecture. And here you see an upper bound of how good one could potentially estimate the depth. You can see that the approach at least goes a certain way in that direction. If you compare this to existing approaches like Synthin, 3D Photo, and so on, you see that if you have large changes between source and target view, that these approaches have a hard time actually completing these scenes, doing the novel view synthesis. If you compare this to our approach that has no depth information provided, you see that it comes up with, so to speak, reasonable, I mean, it's a difficult task, but with reasonable completions for these scenes. The paper then presents a whole lot of comparisons that I don't have the time to go into, where we compare different explicit and implicit 3D representations with depth information, without depth information, and compare the performance that you then achieve when you utilize a powerful transformer model. But to abbreviate, I just give you the conclusion of that so that we don't have to look at the individual numbers. And that is that we've seen a synthesis for strong viewpoint changes based on only a single source view. And this probabilistic model then allows us to represent uncertainties, and with that improves over the state of the art. And here's what I just announced. If you compare various explicit and implicit 3D inductive biases, we see that the transformer models, being so powerful, can implicitly learn geometry without any information about that during training or testing, and that adding explicit 3D information does not give you any significant bias. So in essence, the transformer model learns long-range interactions and does not even benefit if you provided additional 3D information about this. Now with that, I want to show you some unpublished work from my group of on improving transformer models even further. We called that, or coined that, ImageBART, where we combine the transformer architecture with multinomial diffusion processes. And the problem that you typically have with autoregressive approaches is that this autoregressive factorization takes an image and builds this up tile by tile like you would read text. Yeah, and then when you want to generate this cell here, you look at previous cells that you have within your Markov blanket and then synthesize the new scene. But the model misses bidirectional context, and it lacks holistic scene information when rendering an individual part of a scene here. And this, in addition to that, breaks the natural symmetry of images, right? I mean, images are not like text or books. You don't read images from top left to bottom right, other than the tiger hiding in the bottom right would have an easy time catching you, right? Luckily, we perceive images as a whole. And that's where the autoregressive model evidently has some issues. So the question is how you can actually sort of circumvent these issues. And for that, we again start with the VQ gun approach. So you take an image, run this through the VQ gun and get a discrete representation here. And now we do something seemingly strange. We take this representation of the image and we apply a multinomial diffusion process. Now, as you know, diffusion process is essentially destroying information. So you, after some time, will just get a uniform distribution here, much like with this dye added to the water, all the information is gone. Why should we ever destroy information when we want to represent the scene, right? Now we are canceling out this information. Well, the reason is that our actual goal is to turn this process around. Now, once we have destroyed the information, we utilize that to train a transformer model, encoder and decoder transformer, autoregressive transformer, to make up for the information that we've destroyed in this multinomial diffusion process. So in a sense, we're inverting this diffusion process. So you take here towards the right, you have information which is canceled out. Towards the left, you have more information. So you take a representation here on the right, run this through your encoder, and you want the encoder to reconstruct what the diffusion process has canceled out, a little bit like a Gauss-Laplace pyramid. And this then frames a learned Markov chain. Yeah, the multinomial diffusion process is fixed. The Markov chain for reconstructing that is then learned, and that's what we coined BART. And if you ImageBART, if you then attach a CNN decoder on top of that, you can essentially see what the approach does. When you're rendering here in your autoregressive transformer model, an individual cell, you're not only paying attention to all the cells that you've rendered beforehand, but since the transformer encoder is actually utilized on a previous scale, on a coarser scale, this transformer model has already seen the entire image, albeit in a coarser version. So you, in a sense, have a bidirectional context established, because you're not just seeing the cells that you beforehand generated on this particular level of this multinomial process, but also those in the previous and the coarser representation. Now, if you do that, you might wonder, like, okay, now I need to apply the transformer multiple times. Isn't that like more complex in terms of like computational complexity? But the kicker here is that the transformer models themselves can now become significantly smaller. And with that, the typical complexity, it's a little bit hard to compare, but the typical complexity is actually equal or even lower than the Taming transformer approach that I've presented beforehand. So this ImageBART approach established a hierarchical generative compression model with the ability of having high visual quality at a high compression. So if you look at this approach here towards the right, we have a lot of information canceled out. And if you then apply this autoregressive, this generative hierarchical approach several times, you see that more and more information comes in, and you see how gracefully, if you move to the right, how gracefully this information is also canceled out. And what I want you to see here is, or to appreciate here is, that we're not having a blurring a process or something like that, where if you're moving to the right, you're just blurring the image, but you're having, so to speak, like a semantic degradation of the image. Yeah, you're not losing just like resolution of the image becoming smaller, like in the Gauss-Laplace pyramid, but you're losing actually semantic information where the image itself still has the same resolution, the same number of pixels as before. Now, with this approach, you can again do conditional image synthesis, where you condition here on a semantic layout and then synthesize scenes, even better than the Taming transformer approach has done beforehand. You can condition that on text. And render an apple in the shape of a heart, or flames in the shape of a heart, or if you care, the texture of wood, the texture of pizza, or whatever else you crave for. You can guide your in-painting process, which you see here. So you take an image, you mask parts out, and then you condition on this Arctic fox becoming a zebra there, a tiger, a lizard, whatever else you want. And can complete scenes then based on individual text down here, man standing on the road in summer and so on. You turn it into a beautiful sunset. Let me summarize this approach by saying that we've seen that inverting the multinomial diffusion process actually helps us to introduce context in a bidirectional fashion, in a coarse-defined fashion, into transformer models. So in a sense, we train the transformer model by inverting this multinomial diffusion process, and that gives us much richer contextual information. This avoids the unidirectional ordering that transformer autoregressive approaches typically have, and it leads to a natural hierarchical representation of images. And it allows global and local image manipulation, so you can, on different levels, different scales, so to speak, interfere, change the image, manipulate them, and with that enables various conditional synthesis tasks. And with that, I want to close by coming back to the original question that I asked, and that is, how can we learn models that understand the world? And with that, I ask you to look through the eyes of a kid, a little kid here towards the right, and ask, like, what would a kid think about our world? What is this kid thinking here after all? And maybe you would ask like the same question that this kid might ask, like, when are we finally done? Maybe that's on your head or on the mind of this kid. But in this particular scene, I would argue that it's probably something else that this kid might think. maybe is asking himself the biggest question that we could all ask if we were kids in such a scene, and that is, what if? Yeah, what if I had the opportunity to just poke this stack of glasses? I hope you can see this urge that little children in that situation have. And in that case, ask this question and predict the outcome. Now, what would be the outcome if I could nudge this stack of glasses, could nudge this block of this stack of woods here, and then predict the outcome? And then with this physical experiment being done in a more costly or less costly fashion, try to see how good your predictions actually are. And I hope you see that with answering these questions or seeing how good your predictions are, you're getting closer and closer to understanding the world. So in recent work, which is going to come at ICCD this year, which we called iPOKE, we thought about giving users the ability to poke a still image. That is, to drag with a mouse an individual pixel, and then have the user then create a controlled stochastic video synthesis with that. So essentially, you poke, you pull an individual pixel and want the model to then react to that and synthesize possible, plausible completions or videos, in that case, how the entire scene would react if you would pull on the arm of this person here, allow for kinematic transfer from one source person to another person. And the approach should be applicable not just like to human beings, but we want to avoid any prior model like beforehand, any categorical model, so that you can apply it to arbitrary object classes like potted plants here, for instance. So in essence, this requires us to do the following: to learn kinematic interdependencies in the scene. So in essence, if I pull here this leaf of this potted plant, what are the interdependencies? How would other leaves move? And that's what we want to learn. And we want to learn this in a fashion that generalizes to novel objects. So we want to look at a lot of potted plants, see how moving an individual pixel impacts other parts of the plant, and then generalize that to all potted plants, for instance. And here's how the approach works. We have a start frame and a user control, which is poking or pulling an individual pixel. We can also poke multiple pixels, but I find it most interesting to see what you can do with just this very sparse control of an individual pixel. But again, like, feel free to add multiple pokes there as well. And then with that, we want to synthesize the future sequence. What would then happen if I had pulled on the arm here of this person? The standard approach would be you encode your control signal here, and then you try to map this directly onto a decoding of the video sequence. But this is impossible because we have unknown kinematic relationships. There's a lot of ambiguity. Yeah, just putting on this arm, you don't know what the legs would eventually do. There are certain things which are more likely than others, but overall, there's a whole lot of different plausible outcomes. And that's why we want to learn the distribution of all plausible outcomes, which eventually becomes a residual distribution here, which we want to map all the information which is lacking in the control signal on the target outcome. So everything that's not in here to determine the outcome enters into this residual distribution. And with that, we train a conditional invertible neural network, a bijective mapping from this residual distribution into the video domain, conditioned on our steering our conditional signal. So given this control and all the information that you're lacking, you want to map this bijectively onto the target video. And then we utilize a recurrent neural network to make sure that we have temporal coherence, and training works by taking real video sequences and trying to, and then taking individual pixels, like how they move, their optical flow from individual pixel, and trying with that to predict, to reconstruct the scene, its future movement again. And here's some examples. We created a graphical user interface. You can pull on individual pixels, one or several ones, and then synthesize the future video sequence, how the person in that case should move. You can, in that case, You're, however, not supposed to just get a single outcome, right? As I said, it's underdetermined problem. So if you're here injecting a local poke, what we actually provide you with is a sampling-based approach where the approach renders several outcomes by just sampling from this distribution of plausible future sequences giving this individual poke. Here, something for human beings for different data sets. You inject your poke and different plausible outcomes that then actually happen. And with that, we come back to the understanding, and you can do a lot of individual pokes and then see if I poke here where the white cross is and in its vicinity, how do other parts of this potted plant here react to this local poke? And this is what you see here, how much correlation in the motion is. You can do this for every other pixel. You can do this here on a human being. And with that, essentially take individual images, or in that case, then synthesize video sequences and utilize that to understand the kinematic interdependencies within an object without having any 3D model, any model about this object class whatsoever. You're just looking at how objects move, see then, or the model then learns these kinematic interdependencies. So with that, let me wrap up. This model learns these kinematic interdependencies within objects, and key to that is having this conditional invertible neural network that provides you a probabilistic model of all of the kinematic ambiguities. And the invertibility avoids the standard trade-off that previous variational order approaches have, these ones here, between quality and diversity. And the probabilistic nature is very important because it allows you to cope with a very sparse control signal, just an individual poke, and the underdeterminedness. And then you can, from this stochastic approach, you can sample, in contrast to this work from Serge Bélangy's group, where although being sparse, you still need to have a whole lot of individual pokes provided, so to speak. And there's no prior model, which makes the approach applicable to arbitrary object classes and allows it to generalize well to novel instances. So let me summarize. Overall, we've seen that the Taming transformer approach nicely combines the benefits of CNNs, convolutional recurrence for local, representing local context, with transformers for long-range interactions, and therefore leads to a high computational efficiency, which allows high-res synthesis. We've seen that combining the power of transformer models together with this probabilistic representation of uncertainties enables them to implicitly learn 3D structure of scenes without any 3D prior models and extrapolate novel views from just a single image. The combination of transformers with multinomial diffusion, and especially the inverting of the multinomial diffusion process, is a valuable training signal to provide transformers with bidirectional coarse-to-fine context. And last but not least, learning kinematic interdependencies and the ambiguities by means of a conditional invertible neural network helps to cope with very sparse user control to then synthesize movement for arbitrary objects. And with that, I thank you for your attention and my wonderful team who have done all of this work here, and the pleasure that it is for me to work with them. And I'm happy to answer any questions if you have.